Hello, everyone. I'll be presenting our study of the design and operation of Cloud Lab. This study is done by the same group of people who designed, built, and operated the system. What is Cloud Lab? It's a distributed testbed for research in cloud computing and systems research. It's also a place where people, experimenters, use the hardware to build their software environments for experiments in cloud computing and distributed systems. So we view it as a laboratory for working on clouds and not yet another cloud. And here's why we study it. So we want to understand better how the testbed serves the needs of the research community. We want to understand the impact of the design decisions and their trade-offs. And we want to generalize our lessons learned and make them relevant to the design of other testbeds and infrastructure as a service facilities. On the left is the list of objectives that so on the left are the goals that the testbed tries to accomplish, and on the right are the components responsible for helping with those goals. And we're going to do a deep dive in these components in our talk. So come see our talk in track 1 right after the coffee break.
Thank you. Thank you. Hi, good morning, everyone. My name is Romin Pan. This is a 2-minute introduction to our work in the last 7 years. Zanzibar, Google's global consistent authorization system. How do I go back? Oh, yeah. So Zanzibar serves 2 roles. First, it is a storage system for access control lists and group membership. It is used by hundreds of Google products to store permissions on digital objects. Whenever a Google user tries to access a digital object, the product consults with Zanzibar to figure out whether the request should be authorized. Right. It's also an authorization engine that interprets the permissions. Zanzibar is designed to be correct, which may be taken for granted. But the picture actually gets a lot more nuanced when you consider the consistency aspect of correctness. Zanzibar respects the causal ordering of updates to both permissions and object contents. Even if the updates are made by different users on different objects, around the same time, coordinated via a channel invisible to Zanzibar. Zanzibar has a simple data model, but it's also flexible enough to support a rich set of semantics required by our consumer and enterprise products. Zanzibar needs to protect billions of objects shared by billions of users. It stores trillions of echo entries and serves millions of authorization checks per second. It is also deployed around the globe to be close to its clients and our end users. Last but not least, as a system on the critical path of user experience, Zanzibar needs to be both fast and reliable. Zanzibar has low tail latency and has maintained 5 nines of availability over the last few years. To learn more about Zanzibar, please come to our talk in track 1. We look forward to seeing you there. Thanks.
Thank you. We skipped the talk before this one because there was no lightning talk for that one. Next, we have the IASO.
How do I move? So it's just... Oh. Hello. Very good morning to one and all present here. My name is Deepthi, and I'm going to be giving the lightning talk for IASO. So IASO is basically a system that we built that can handle a class of failures that are not commonly addressed. And fault tolerance is basically a very important aspect to keep in mind while designing distributed systems. But common distributed systems are usually designed with what we call a fail-stop failure model, wherein we assume that a faulty node is going to be completely down. But recent research reveals another form of fault another class of faults called the fail slow. So here what happens is that a faulty node does not completely fail. Instead, it just functions at a much lower performance than expected. A cluster that is designed for fail stop will not be able to detect a fail slow fault and can lead to a complete cluster outage. This class of failure is not very uncommon, as seen in work in 2018. We see that across 12 institutions, there were nearly 101 instances of such fail slow faults that could cause complete cluster outage. In our own study that we did at USENIX, that spanned about 39,000 nodes, we saw that the annual failure rate for such fail slow faults was 1.02%. These kind of fail slow faults are also extremely difficult to detect. That is mainly because of the large number of root causes. In our own study that spanned 1.5 years, we saw around 30 different possible root causes for fail slow faults. And again, recent research proves that these faults are seen even in very common open source distributed systems, such as Zookeeper and Cassandra. To handle such fail slow faults, we built a system called IASO. IASO is picked from the Greek goddess of healing. So it's a peer-based, non-intrusive fail slow detection and mitigation framework. So after deploying IASO, we studied its performance for about 1.5 years across 39,000 nodes. And we see that it could accurately and quickly determine the presence of a fail slow fault and mitigate it. Come check out our paper presentation at 12:20 on track 1 for a more detailed design and architecture overview of IASO, and also a statistical analysis on how fail slow faults look like in real production deployments.
Thank you.
What's up? My name is Chris. I'm going to talk about scaling the distributed actor runtime with Partisan. So distributed programming is still very difficult. Everybody here is probably doing it today in some form or another. And kind of the three main problems that we have to focus on are around state management. When we add concurrency, state management gets very difficult. This is pretty straightforward. And then ideally, we want to take advantage of all the available parallelism that we have. Since this is very hard, a lot of people have turned to distributed actors because they're very good, and they're a very good match for distributed systems. They have state encapsulation, they are pervasively concurrent, and they have a messaging model that's very similar to what we assume in distributed systems, unidirectional asynchronous messaging. And some of these apps that they've been used on, you might have heard of: Call of Duty, WhatsApp, Halo, Gears of War, Fortnite. These are not small applications. But the problem is today there's two main drawbacks with distributed actor systems. The first is scalability, because these systems assume that all the nodes have to talk to all the nodes in the cluster, which can be prohibitive at scale. And latency, because we use a single TCP connection to connect all of the nodes and send information through multiplexing. This reduces the concurrency and parallelism of actors and can lead to problems with head-of-line blocking, network latency, queuing delay, and contention for shared access to the network. And so today we're going to talk about a system called Partisan. It's a design of an alternative runtime system. We've prototyped and implemented this in Erlang. It allows users to specialize the communication to the application, which allows this to be done without change to application code and done at runtime. It provides reduced latency and increased scalability by parallelizing message sends on the network. And the results show that we have an order of magnitude increase in cluster size, 13.5x reduction in latency, and up to a 38x improvement in throughput. So we are batting in the leadoff spot of track 2, 1120. Please come to our talk. Thank you.
Thank you. Great. Next, we have the unleashing the power of learning. Okay, sorry.
Hello, everyone. The title of our paper is Unleashing the Power of Learning, an Enhanced Learning-Based Approach for Dynamic Binary Translation. Dynamic Binary Translation, or DBT for short, is a key enabling technology. Typically, DBT systems translate binary code using manually constructed translation rules. However, manual construction of the translation rule is a significant engineering effort. So our previous work proposed to automatically learn binary translation rules. This is inspired by the observation that the binaries compiled from the same source code are semantically equivalent. Although this approach sounds attractive, it still has some limitations, such as low success rate, limited translation coverage, and inefficient binary code. After further investigation, we found the main problem comes from the strict equivalence verification during the learning process. This can cause many high-quality translation rules discarded. So in this work, we propose an enhanced learning-based approach with constrained equivalence verification. That means even if the translation rules are not strictly equivalent, they can still be learned and applied to achieve higher translation coverage and generate more optimized binary code. You may wonder, is it really possible to use this approach to harvest more translation rules? How can we guarantee the correctness when applying constrained equivalent translation rules? Can these translation rules really generate more optimized binary code? Please come to my talk, and I will show you how. Thanks.
Thank you. Next, we have Transactuations, one of the Best Paper Award recipients.
Good morning, everyone. I'm Aritra. Good morning, everyone. I'm Aritra. Let me introduce you to our work called Transactuations, where transactions meet the physical world. This was work done at Samsung Research with my former colleagues Tanakon, Masood, and Caesar. So in this talk, I'm going to focus on one fundamental aspect in IoT and one of the overlooked aspects in IoT, that is reliability in IoT systems. So why do IoT systems need to be reliable? Let me give you an example of a dissatisfied smart home customer. He was on vacation and his home got robbed. He found that the logs showed that the motion sensors detected the motion of the intruder, yet the application did not sound the alarm. And he lost trust in the system. And not only this customer, there are other customers who lost faith in the system and says that he would no longer trust the system for anything serious, for example, like security. We delved deeper and found that the root cause behind these inconsistencies is the inconsistency between the physical state and the application state. And this happens due to various kinds of failures in a smart home environment. The failures could be device failures, network failures, and even concurrent execution. We analyzed over 180 odd applications across 2 smart home platforms and found nearly 309 potential problems due to inconsistencies that arise out of failures. Now, how to solve this problem? Well, the main problem in this domain is the lack of a proper programming abstraction, which makes it difficult to write programs. Transaction is a good programming abstraction, as it provides all or nothing semantics and also isolation semantics. However, we found that it is impossible to adopt transactions as is because of the nature of the IoT environment. So we introduce our new abstraction called Transactuation, which allows the developer to program in a failure-aware way. It provides strong semantics for systems that interact with the physical world. If you are interested, please attend the talk in the next session on track 2, session called Runtimes. Thanks.
Thank you. Next, we have Not So Fast. This is the last talk in the Runtimes session.
Hello, everyone. I'm Abhinav, and I'm going to give you a brief introduction of our work on first large-scale performance evaluation of WebAssembly. So WebAssembly is this new binary format to which you can compile your native applications and run them directly inside a browser. So since its release, WebAssembly has been used to run a wide range of applications directly inside the browser. The paper that introduced WebAssembly did some evaluation of WebAssembly using Polyben C benchmarks and find that WebAssembly is only 26% slower than native. However, these Polyben C benchmarks are actually a suite of small scientific kernels, and hence they are not a representative of WebAssembly use cases. Spec benchmarks, on the other hand, are a better representative of these use cases. But we just cannot compile spec benchmarks to WebAssembly and run them in a browser because they require a system call interface, which is not available in a browser. To solve this issue, we developed BrowsixWasm, which is a Unix kernel running inside a browser. And in my talk, I'll be talking about some of the design issues we faced while developing BrowsixWasm and how we made sure that BrowsixWasm's overhead over spec benchmarks remains minimal. Finally, we were able to compile and run spec benchmarks in browser in WebAssembly and find that, unlike prior work, it is 55% slower than native. We also analyzed the performance counter data that is generated using by executing these spec benchmarks and find that WebAssembly is slower because of some missing optimizations, some of the design issues that are inherent to WebAssembly, and some of the restrictions supplied by the browser environment due to which the JIT compiler is not able to do some optimizations. To know more about our work, please come to our talk in the runtime track. Thank you.
Thank you. Next, we have the file systems track, and the author for the first paper is on a plane right now, so we kindly agreed to show the YouTube video that they had submitted. And this is my cue to also advertise the fact that on the website, when you look at every single paper, in the resources, you can find actually YouTube links to the lightning talks. So if you want to remind yourself what the paper was about, or if you want to remember or learn about a track that you could not attend, that would be a good way. So let's go with this one.
Hello, my name is Aasheesh. I'm a PhD student at Georgia Tech. I'm presenting my work on improving the performance of user file systems. User file systems offer better security and system reliability. They are easy to develop, debug, and maintain. However, they perform poorly. Fuse is the state-of-the-art framework for developing user file systems. Over 100 file systems have been written using Fuse. Under Fuse, all file system requests are served in user space. We evaluate performance of Fuse using Linux compilation workload. Despite all optimization, Fuse reports a high overhead compared to ext4. The main cause of performance overhead is context switching and data copying that occurs while serving file system requests in user space. As seen from chart, we see a lot of context switches to user space for kernel compilation workload. Therefore, if we reduce the number of context switches to user space under Fuse, we can improve its performance. This is exactly what we do in this work leveraging eBPF framework. eBPF allows applications to insert custom code in the kernel and safely execute them under a virtual machine runtime. eBPF is a part of the Linux kernel and is used by perf, tracing, and networking subsystems. We integrate eBPF with Fuse to provide EXTFuse framework for user file systems. Under EXTFuse, developers can insert custom code in the kernel and serve file system requests right in the kernel without incurring any context switches to user space. We consider the same kernel compilation workload for evaluating EXTFuse performance. As seen from the graph, it performs at par with ext4, and this is because now fewer requests are now delivered to the user space. Since EXTFuse allows custom code to be safely executed into the kernel, it opens up a number of opportunities for optimizations. Please refer to our paper for details. Thank you.
Okay. Okay. Next, we have flex group volumes.
Hola, me llamo Jason y estoy aquí presentar. Oh, wait, this isn't the Democratic presidential debate here. I'm sorry. My name is Jason. I'll be presenting Flex Group Volumes, a distributed file system built by NetApp. While many approach building distributed file systems from the top down, We wanted to go bottom up with our existing local file system, Waffle, instead, in order to preserve its high performance and reliability while minimizing the overhead introduced by distributed operations. So NetApp's filer historically served volumes over NFS from a single server. ONTAP clusters introduced the ability for clients to mount a volume from any cluster member, routing requests over a fast cluster interconnect if needed. Clusters also brought the ability to manually connect internal volumes across multiple nodes into larger client visible volumes. Now, ONTAP provides a distributed file system called Flex Group Volumes. A Flex Group is internally composed of individual Waffle volumes, which it then presents as a single volume to the clients. The system automatically manages the placement of files and directories to spread the load across the capacity of an entire cluster. We wanted to avoid the latency overhead of a metadata service, so the individual volumes store file and directory metadata, which may include remote links to other volumes. Remote links connect directory subtrees across volumes into a single file system namespace. There are two key components to make this work. First, we created a remote access layer to ensure atomicity when manipulating remote links. Second, we use heuristics to determine where to place each new file or directory. Our goal is to balance the cluster and the cluster load and disk usage while minimizing the number of remote links and their overhead. We show here the performance of 3 SFS workloads on increasing cluster sizes. Flex groups scale well and have been commercially successful with thousands of flex groups deployed to manage hundreds of petabytes. We hope you'll join us at the talk and check out the paper, and it'll be exciting enough to keep you awake after lunch. Thank you.
Thank you. Next in the file systems track, we have ERO-FS.
Hello, everyone. So today I will talk about our work, ERO-FS. So smartphones is our life now. We want to store everything in your phone. And no one wants to see such a warning saying that there's no enough space. However, system resources are consuming more and more storage in your phone. Well, the good news is that the system resources are read-only, so that we can use compressed read-only file system to store these system resources and release more space for users. SquashFS is the state-of-the-art compressed read-only file system, and we use it in Android, and the system booted and it lagged and even froze for seconds and then rebooted. So why did this happen? We find that SquashFS used the fixed size input compression, which brings 2 issues. The first one is that it causes read amplification, and it also introduces massive memory consumption during the decompression. So to solve these 2 problems, we introduced ERO-FS, which uses fixed size output compression, and which can reduce the read amplification. We also propose 4 kinds of decompression approaches, which can reduce the memory consumption during the decompression. In the real-world deployment, ERO-FS saves more than 30% storage used by the system resources, and it achieves comparable or even better performance than ext4. ERO-FS has been upstreamed to Linux kernel and is running on tens of millions of smartphones. If you are interested, welcome to our presentation this afternoon. Thank you.
Thank you. The last talk in the file systems track is QZFS.
Hello, everyone. My name is Xiaokang Hu. I'm going to talk our work QZFS, Creative Accelerated Compression File System for application agnostic and cost-efficient data storage. High-performance computing requires high-speed storage I/O, which can be provided by NVMe SSDs. But the high price greatly increases the total cost of ownership. Data compression is an effective solution to achieve space efficiency and reduce cost. but the benefit comes at the expense of CPU resources, leading to the advent of all kinds of compression accelerators for offloading. Data compression could be integrated into different system layers, including application layer, file system layer, and block layer. Our work investigates ASIC-based compression offloading at the file system layer using Intel Quick Assist technology. It's a modern ASIC for cryptography and compression, with performance up to 100 gigabits per second and price low to $32 after putting into chipset. The proposed QZFS is designed to transparently benefit all applications running on it, featured by high performance, high space efficiency, and low CPU utilization. Design highlights include seamless integration of QAT accelerated gzip, the vectored I/O model for data reconstruction without incurring memory copy, hardware-software switch that considers offload cost, and compressibility-dependent offloading to save QAT resources. In future, we may provide async offload framework to further enhance system performance. If you are interested, come and check out our presentation at 3:20 p.m. track 1. Thank you.
We're moving to the next track, which is Big Data Programming Models and Frameworks. The first talk is about Apache Nemo.
Good morning. So this is the lightning talk for Apache Nemo, a framework for building distributed data flow optimization policies. Nemo policy optimizes distributed scheduling and communication of big data pipelines. So big data applications are typically expressed as these high-level transformations of data collection objects, and these applications are compiled into a directed acyclic graph or a DAG to be executed by a distributed runtime. And in this work, we're interested in optimizing the scheduling and communication strategies of this pipeline execution. And the existing approaches are either application level or runtime level. And runtime level approaches, they allow for direct modifications to the runtime DAG and provide fine control over scheduling and communication behaviors. However, they do not ensure that the optimized execution produced equivalent results as the original execution, whereas the application level approach ensures the correctness. However, they do not provide the same level of fine control. So our approach is to take a middle ground between the applications and the runtimes and express optimizations as transformations of an intermediate representation. So Nemo is our system that embodies this idea and comes with these three system components. The intermediate representation DAG provides transformation methods that provide both correctness and fine control. And we introduced this notion of an optimization path, which is simply a function to transform the IR DAG. And we also have runtime extensions to apply the optimizations in the underlying runtime. And we've evaluated Nemo in various deployment scenarios, including transient and geo-distributed resources and large and skewed data. And the results show that Nemo is on par with specialized runtimes that are tailored for these specific deployment scenarios and further improves performance for scenarios with combinations of different characteristics. So our talk starts at 2:20 p.m. today, and please come to our talk to learn more about Nemo. Thank you.
Thank you. Next, we have Tangram.
Hello, everyone. The main idea of our work is to bridge the mutable and mutable data abstractions through a new programming module called map update. So we can roughly classify existing offline data analytics frameworks into two categories according to their data abstractions, immutable or mutable. So bulk processing systems like Spark generally adopt the immutable data abstraction, and let's call them immutable systems. In contrast, machine learning systems and graph analytics systems usually adopt the mutable data abstraction, and let's call them mutable systems. So immutable systems usually provide better support for failure recovery and load balancing, while mutable systems are more efficient for iterative workloads because of their support for the in-place state updates and asynchronous execution. So we find that existing systems either adopt the immutable or mutable data abstraction and do not enjoy the benefits of both worlds. This motivates us to propose a new programming model called map update. So this is a programming model with a similar syntax to MapReduce, but it supports a mutation on data collections. And programs written in map update allows the system to determine automatically the mutability of a data collection. This feature allows map update to express a wide range of workloads, including bulk processing, machine learning, and graph analytics naturally. And most importantly, map update enjoys the benefits of both immutable and mutable data abstractions. By supporting the iterative and asynchronous execution, as well as adapting different fault recovery strategies to different failure scenarios. For more details, please come to our presentation in track 2 this afternoon.
Thank you. Next in the big data programming models and frameworks, we have Struts AP.
Hello. Hello, everyone. Let me start. Distributed machine learning programming is a difficult task. To simplify this task, we can use high-level frameworks. But converting a sequential machine learning program into a framework program still requires substantial engineering effort. Today, I will present a new framework, Struts AP, that allows you to convert a sequential machine learning program into a distributed machine learning program almost mechanically. Targeting ML applications follows a specific structure and characteristics. Our targeting ML applications have two parts. In pre-training part, we store the input data and the model parameters using sequential data structures. But these sequential data structures definitely have a limited scalability. The training part has a nested loop statement. And here the inner loop of this nested loop statement is the source of parallelism. We are going to parallelize this inner loop in a cluster. But the challenge is that there might be data dependencies among loop bodies. Converting this sequential ML program into a Struts AP program requires minimal and mechanical changes to the sequential ML program. First, we replace the sequential data structures with our distributed data structures that provide the same interface of the sequential data structures. Then, we replace the inner loop statement with our parallel loop operator that parallelize the loop bodies with a strong or relaxed consistency depending on user configuration. Then this annotated program is pre-processed by our compile time tool and compiled into a binary program, and finally it's executed in a distributed environment by our runtime system. For more details, come to my talk at 3 p.m. today. Thank you.
Thank you. Thanks. The last talk in this track is Sophia. Wow. Oops. Sorry. interesting.
Hello, everyone. This is Ashraf Mahgoub. This is the lightning talk of our paper, Sophia, that targets online reconfiguration of clustered NoSQL databases for time-varying workloads. So first of all, we discuss what are the challenges for online tuning of NoSQL databases. And the first challenge is that databases have a plethora of performance-related parameters that needs to be tuned for optimal performance. And for real-world workloads, the workload characteristics is always changing over time, and therefore there needs to be reconfiguration for the new optimal parameters. So our target is to reconfigure clustered NoSQL databases in runtime, such as Cassandra and Redis, for globally optimized performance, as well as maintaining data availability and consistency requirements. And this is where all the related work that we compare to in the paper fails. So in this very brief example, we show how the ops per second observed from a cluster of 2 Cassandra servers is it changing over time when we apply reconfiguration. And the takeaway of this figure is that reconfigurations has cost, transient cost to performance, and there has to be some knowledge about how long the new workload will last, and then we can decide whether a reconfiguration will be globally optimized or not. And this is where our solution comes in. Our solution performs cost-benefit analysis to achieve long-horizon optimized performance, as well as it applies a distributed protocol to gracefully switch over the cluster so that we always maintain consistency and availability guarantees. We apply our evaluation to 2 popular databases, Cassandra and Redis, and we use 3 different dynamic workloads in our evaluation, and we compare to the default configuration of every database and the static optimized configuration, and every configuration that always changes the parameters as soon as the workload changes, as well as an autonomous database named ScyllaDB. If you are interested, please come to our talk in the track of big data programming models and frameworks. Thank you.
Thank you. The next sessions, we have 2 tracks. The first track is invited papers. For those, we do not have lightning talks. So we are going to the first security session of the conference on kernels. Okay, let me.
Hello everyone, I am Seon Park, and this is a brief talk about our work, software abstraction for Intel Memory Protection Key. So Intel Memory Protection Key is a hardware security feature which is available from Intel Skylake SP processor. It provides fast permission change for page group with single instruction, and also it can provide executable-only memory in hardware level. Broadly speaking, Intel Memory Protection Key consists of 3 components: protection key field in page table entry, and protection key write unit register, which store permission for page groups, and instruction set such as write pcarry and read pcarry, which assist the pcarry register. To utilize MPK for memory protection method, we need to address these 3 challenges. First, key is after-free, which can be a potential security hazard. And second, non-scalable hardware resource because of the hardware limitation. And third is the asynchronous permission change. So to address these 3 challenges, in our work, libMPK provide key virtualization by decoupling physical keys from user interface and support key indirection. Also, we provide permission synchronization API. So in our evaluation, we apply libmpk to these applications, OpenSSL and Memcached and JavaScript engine to protect different type of target. And libmpk shows negligible slowdown to protect memory region. So to sum up, libmpk is secure, scalable, and synchronizable abstraction for MPK. For detail, please come to our talk this afternoon. Thank you.
Thank you. The next talk in this track is effective static analysis of concurrency use after freebox in Linux device drivers.
Hello, I'm Jiaji Bai from Tsinghua University. I'm very glad to introduce our paper. User-free bugs in device drivers are often dangerous. And some of these bugs are caused by sequential code execution, namely the free and the use are in the same thread. And some of these bugs are caused by concurrency code execution, namely the free and the use are in two different threads. So they are more difficult to detect. Concurrency user-free bugs in device drivers are harder to trigger and reproduce at runtime, and they can lead to system crashes or security problems. We studied the Linux kernel commits and found that 42% of driver commits fixing user-free bugs involve driver concurrency. We also studied the mentioned tools in these commits, and we found that no static analysis tool is mentioned to detect concurrency user-free bugs. So it is important to explore static analysis to detect such bugs in device drivers. However, there are some challenges to do it. The first one is how to identify driver functions that may be concurrently executed. The second one is how to ensure accuracy and efficiency of code analysis. In our paper, we propose our approach named DCUF. It uses a local global strategy to extract driver functions that may be concurrently executed. Then it uses a summary-based log site analysis to detect concurrency user-free bugs. If you want to know more about our paper, please come to our presentation. Thank you.
Thank you. Next, we have Alex Dees.
Good morning. This is Vikram. If you see, the kernels are everywhere, right from smart devices to IoT segments and data centers. Even this room is filled with a couple of screens. With a few tries, you can crack the password. So why is this inherently insecure? Because commodity kernels are historically monolithic, with the kernel and its subsystems such as network, device drivers, and file systems all run in a shared address space, where a vulnerability in a single component could potentially compromise the entire kernel. One solution is to provide isolation, where we split the monolithic kernel into isolated components to confine faults within the affected component. However, there are a lot of challenges for isolation to be brought into a monolithic setting. We present a generalized framework called lightweight execution domains, where we provide general abstractions for isolating device drivers in a monolithic environment, with the following design goals. First, we need to be able to reuse the code that is existing in the monolithic environment, because we don't want to be developing anything from scratch. And to provide isolation guarantees, we should be able to run two separate domains and two separate copies of data structures. And we should be able to have a way to synchronize these objects across domain boundaries and to have a unified view of the data structure. Our framework offers inter-process communication to communicate between the isolated and non-isolated parts of the code, and an interface definition language to be able to run unmodified code under isolation, and an asynchronous runtime to better utilize the CPU cycles using our IPC mechanism. We evaluate our framework on 2 software-only device drivers and a 10 Gbps Ethernet driver. And we ran iperf benchmarks for packet transmission and we experience an overhead of 6 to 13% compared to the native driver. If you are interested, please visit our talk this afternoon in the kernel security session. And if you are more interested, please visit our poster session. If you are even more interested, please talk to me about funding our project. Thank you.
Thank you. Our last lightning talk is about jump switches. How is everybody doing? Great.
Okay. So I will briefly present our work on jump switches. Well, you've probably heard about the Spectre vulnerability. The main problem that causes this problem is that CPUs try to execute instructions as fast as possible, but from time to time they encounter instructions that prevents them from knowing what the next instruction should be. And in this case, they use a branch predictor. The branch predictor might misspeculate, and we are told not to worry, but the problem is that those instructions that are speculatively executed might have side effects, and a malicious user can manipulate those instructions to leak data back to the malicious user that it should not know. In the case of Spectre v2 that our study deals with, indirect branches, like those that are being used in function pointers, can be manipulated to run arbitrary code that leaks data back to the user. Now, luckily, there is a solution, not ours, that is called RedPolin. And the solution is to emulate these kind of indirect branches using other instructions, but the impact of this solution is that every indirect branch in the system results in a misprediction. We want to deal with this problem, and we developed jump switches. Jump switches are a dynamic indirect branch promotion mechanism that learns targets of branches on the fly and does binary rewriting of indirect branch promotion code. It supports multiple hard targets and targets that are different per context, per process. We implemented our solution on Linux, on the Linux kernel, and we show performance improvements of up to 10%, which are 2% next to the performance of native systems before Spectre v2 was introduced. Hopefully, I'll see you in the session of security number 1.
Thank you.